the star very much look like, you know, a Christmas tree ornament when it's overexposed. It's so bright. And the trick here with Hubble was to remove the star, which was done very precisely. And the student here is doing that too for his dissertation, and either find surrounding planets or finding the original debris disk, the disk of gaseous material of which the planets are formed. You can see, lo and behold, this one here has 3 planets picked up by Hubble, and then one more in a later image, as we'll see with the LBT telescope in Arizona. The James Webb Space Telescope will do this much more precisely. Will, for much fainter stars, subtract the images very carefully and find surrounding planets much more further away, or also see occasions where these planet systems form. So one way to form these exoplanet systems, of course, is in this collapsing gas cloud, where first the star forms and then the surrounding material sort of swirls around and quickly settles into a plane because of the law of conservation of rotation, as we call it, and then eventually end up with a planet that goes around the star. And under lucky enough conditions, you will see that the planet itself will sometimes go in front and sometimes behind the star. Now, this may take only a few days or a few months, depending on exactly how far that planet is away from the star and the viewing angle. Of course, you have to view it just right. But if you view that, you look at the total light from this planet, you'll see that normally it's, you know, 100% in some arbitrary units, and then as a function of time, sometimes it goes down to 98% with some noise, but you measure it many times to get it quite precisely, and then it goes back to 100%. And this ingress and egress, as we call it, where it starts dimming and starts brightening again, of course, is precisely where this planet plus its atmosphere goes in front of the star and then goes away from it again. And then when this shallow sloped dimming and brightening happens is precisely when the atmosphere first starts occulting the star or starts moving away from the star again. And if you take a spectrum of this entire, this is, by the way, how these exoplanets are discovered. If you take a spectrum, this gets a little technical, but this is about as technical as it will get, a little chemistry here for the chemistry students amongst us, is that if you look at the function of wavelength from bluer infrared to redder infrared colors, you can see the brightness of the light will show these characteristic dips, and then another dip here. This dip is due to water, which is more abundant. This dip is due to carbon dioxide. This is again water and carbon dioxide. So you could, and this is a simulation, but this is in principle what you could observe in about a day of integration time of the, on the atmosphere of an Earth-like exoplanet that goes around the star like the sun. It will take a whole day. And you need to repeat it, you know, a couple of times over a period of a month or so for that planet that it goes around its own star. But if you're lucky, you can in fact see these elements, especially if you find water and carbon dioxide. And there's ozone in here somewhere too. If you find ozone, of course, this is a simulation, then you might have found a planet where life is possible. So now I'm going to the third topic of the galaxy assembly and supermassive black hole growth. So if you have any questions on the previous topic, I'd be happy to take some now, or we could just move on and take questions at the end. It's hard for me to see any raised hands, so either speak up or otherwise we'll take them at the end. But now I'm going to talk about galaxies and supermassive black holes. So galaxies, as Gary Williger explained yesterday in his wonderful talk at the restaurant last night, they come in this tuning fork scheme of classifications that was also invented by Mr. Hubble. Very roundish, football-shaped galaxies. They're a little bit more oblong, called ellipticals, tend to be also a little more massive. Then spiral galaxies, which tend to come either very loosely wound spirals or very openly wound spirals. This is, very tightly wound spiral arms like here. And in some cases they come straight spiral arms, in some cases they come with spiral arms and a bar in the middle. And the important point here is that Mr. Hubble in the 1920s found that when the redshift, when the universe was at the current age, so about 13.7 billion years old, he didn't know that back then, but basically what we call it zero redshift means the universe is expanded to today's present size. You see 40% ellipticals, 50% spirals, maybe a bit more, and about 10% irregulars that he didn't even bother to plot here. I call them train wrecks. Hubble, the telescope, in the 1990s, at the redshift 1 or 2, the universe had expanded, only twice, half as much as today. So this is roughly an indication of how much smaller the universe was back then and how much younger it was by roughly the same amount. There were only 15% ellipticals and 30% spirals, and the rest, more than half, were train wrecks. And that's a very important data point, because it shows that galaxies form over time, and they form these beautiful spirals, but not instantaneously. It takes billions of years, and they started out with smaller pieces that had to come together that initially didn't look like much. Here's the spiral galaxy, Messier 83. It's about, let's see, I think it's about 15 million light years away from us, so cosmologically speaking, quite close. And you see inner part of the galaxy here is one of the spiral arms coming out of the center. This is the center here. If you squint really hard, you can also see some of these pillars of creation there. So there's, again, hot and young stars, cosmic fraternity members, if you wish, that are shining onto these regions and making new stars like the sun there. And then there's all these regions with this reddish hydrogen gas and all this darker material out of which new stars are formed. This is basically hydrogen gas and dust that in various pockets, such as here and there, makes these new star clusters of young hot stars that then blow their own holes and start shaping the surrounding materials where the lower mass stars like the sun are forming. So this happens everywhere. Stars form everywhere. The bright luminous ones first, and then they shape the rest of the material and form the rest. Now on the context of elliptical and spiral galaxies, they do not often come alone. More often than not, they come in pairs or triplets or groups or even clusters. And sometimes they look very reddish, like these older elliptical galaxies, or in this case with some residual spiral arms. Sometimes they look like they're almost entirely blue because they got so many hot and young stars, and the number of reddish older stars is not so clear. This is the Stephan's Quintet. This galaxy happens to be in the foreground, but the rest is about 40 million or so light years away. And these are indeed 4 fairly sizable galaxies like our own. Our own galaxy would look just like that are in the process of merging. They're at the same distance, they're colliding, and a few billion years later they will, look like this, and like the Antenna Nebula galaxy, and they will start basically tearing each other apart. So these were originally 2 disk galaxies, and now they are sort of tearing each other apart, and they will form one giant galaxy in a billion years or 2. This is apparently very common in the early universe. It's not very common right now anymore. You have to look really hard to see lots of those. Hubble has imaged a number of these things, but there's not too many of them today. But almost all galaxies way back then, as we'll see, look like that, because they're in the process of gobbling up their neighbors. In fact, we have our own neighbor. And by the way, a galaxy is a collection of stars, like our own sun, about 100 billion of them. I used to be able to say 10, 20 years ago in my public talks that there were about as many stars in the galaxy as dollars in the national debt. That is unfortunately not the case anymore. There is more dollars in the national debt than stars in the average galaxy, but that's not the fault of the galaxies. Sorry, I didn't mean to make political statements here, but it's always a cute joke. And so the Andromeda galaxy here, which you today can see, this would be a picture you could take today in a clear sight across the mountains. There's the Milky Way that we heard about earlier. There's the Andromeda galaxy, the nearest neighbor. And that's what it will look like in 2 billion years, 3 billion years, 4 billion years, 5 billion years. And it's actually approaching us. It's a little bit bigger than us. It's not only approaching us. With Hubble, even back then in 1920, he knew that the redshift of the Andromeda nebula is a negative sign. It's really not moving away from us, it's approaching us. And so Hubble, the telescope, 70 years later, not only discovered that it's moving towards us, but there's really no lateral motion. So if this is our galaxy, this is Andromeda, it's not going to just fly by, but it's actually going to collide, smash on, right? And so that's what will look 2, 3, 4, 4.5, 5 billion years from now. And in a good 5.5 billion years, that galaxy, which is now Andromeda and us, ain't no longer a spiral. Gone is the Milky Way. This is a giant elliptical. So I was talking to Laurie about this earlier. This is not necessarily time to worry about selling your real estate just as yet. In fact, other disaster will happen before that time, like the sun will run out of fuel. But 5 million years from now, you know, who knows what will happen to our neighborhood. And again, this is today fairly rare, but long ago it was very common. So these are a couple of other examples of galaxies that are merging nearby. I call them like the corporate mergers on Wall Street, right? Wall Street hasn't been doing too well the last few days, but we'll get to that later. Something similar happens in the galaxy stock market. You know, small galaxies merge and form bigger galaxies, and big companies gobble each other up. Back in the heydays of galaxy formation, we're now talking 5 or 10 billion years ago, this was more common than an exception. You didn't see any spirals or ellipticals to speak of. All you saw was these funny looking train wrecks. More often than not, they look extended. They're like tadpoles. We call them tadpole galaxies. One of my students at ASU did a dissertation on that. And they're like basically two blobs, much smaller than Andromeda and our own galaxy that were, you know, flying by once, maybe like an harmonic oscillator, eventually just basically collide. And there are some students here who've done some simulations of that with Lutz and his research group. And so JWST will measure this all much better at the larger distances and higher redshift. So let's get to that, what JWST will actually see. It will see these very deep fields. Now this is not a particular deep field. It only took a couple of hours to do with Hubble, but it was done in 10 filters. And so there's some of these giant galaxies in the foreground, which are not unlike our Andromeda and Milky Way galaxy. And then there's all these faint galaxies in the background. Now you're looking down here to a level of about 27 magnitude, which is astronomers' jargon for saying it's about the brightness level